Okay, so we're going to be in the hydrosphere unit now. So whenever you see this, it'll be HKQ whenever you see the different designations on the calendar and such. The first one's going to be 3.1. The first section in the hydrosphere is 3.1, storage and transfer of water. I know we've done a lot of work already on the case studies. I think when I wrote this blog, I usually did the lecture and then we did the case study, so you might see some stuff saying you're going to see this in the case study later, but you've already done those. So it's good though, and we will get started with 3.1.1, which is the main, with key question 1, the main storage zones of water. So I'd like you guys all to watch this video, so do that on your own. It's an introduction as to how water is distributed globally, where it is and what form it's in, salt water, fresh water, you name it. It goes over all that. It's a pretty quick video. It's a pretty cool visualization from NASA. So where is our water? Now we know that 97% from that video you'll find out is 97% of our water that we have on Earth is salt water that we can't use. So we only have 3% that's fresh. And when I say we can't use, I mean you can use it for different things, but for most of our industrial processes, all of our agriculture and our domestic use, we can't use salt water. So unless we use desalination, which we'll talk about later, which is very expensive. So we really want to focus on that 3%, which is fresh water. Unfortunately, most of that is also not usable. So let's take a look at that. Fresh water is 2.5 or 3%. Now 68.7 of that is in glaciers and ice caps, and so that's fairly unattainable unless you were to go up and melt that. But again, that would require energy, and energy requires fresh water in order to generate that, we'll see. So you'd have basically a net loss of fresh water to get that fresh water. So really getting it out of the ice caps and glaciers is not a good solution. 30.1% is in groundwater. We do use that. 1.2% of, now remember this is not of all the water, this is just of that 2.5 or 3%. So 1.2% of that is in surface and freshwater. Now of that, the surface freshwater, we've got ground ice and permafrost, then 20.9%, so 69%, that's hard to get as well. 20.9% in lakes, that's fairly easy to get. Some of it, 3.8% of that's in soil moisture, swamps and marshes. Rivers is a very, very small amount due to, they're compared to lakes and all that kind of stuff, they're very narrow and not as deep usually. So rivers, while we talk about them a lot and we use them a lot, the amount of water that they contain isn't a huge amount. And then there's some in the atmosphere and also in living things. So how does it move around? Now, the thing about the water is that it's a much quicker cycle. It is called the water cycle. I'm sure you learned about that in elementary school. Or we call it here the hydrologic cycle. You have a lot of different processes, and you may have learned a song about that or something like that in elementary school. But the nice thing about it is a much quicker process than, of course, like coal generation, where it takes millions of years to get it to the state that we can use for energy, or sorry, thousands, hundreds of thousands of years. But when you look at the water cycle, it happens fairly quickly, but it doesn't matter. If you take it out faster than it's recharged, you will dry it up. So what we've got here is we've got oceans, and we can start anywhere you want on a cycle. There's no start, but we're going to look here first at the oceans. Big, vast, open oceans are going to have evaporation. Evaporation is where your liquid turns into the gas phase. You will then have precipitation in a few different places. You can see in the middle, and the right, and the left. Precipitation is when it gets high enough and it attaches to some kind of particle in the air, condenses. When it gets high enough, it'll get cool enough that will condense back to liquid water and will fall down, but it has to form on something. So usually some kind of dust particle will bring that down, and it comes down as rain. If it comes right back down to the ocean, it just falls into the ocean. If it comes back down, as you can see in the middle on the land, it's going to come down as precipitation, which will come down as rain and come off. If it happens up high enough, it can come down, or if it happens in cool enough weather, it can come down as snow. So that's what we have there. We have the precipitation coming down here, here, and here. You also have that coming off. What does it do once it gets onto the land? It can form ice, snow, and glaciers that you can see on the left. Permafrost, which is like frozen soil. Eventually, that will melt. When it melts, it's called runoff. The runoff basically is just basically the water running on the ground and going to its lowest point. Water always flows downhill, so always go back into the ocean or may form a river. If it runs over the same path over and over again, it might dig into the ground and form your rivers and your streams and your lakes. So you get a lot of rivers there. The river will usually discharge into an ocean or a gulf or a lake, which is what happens there. And so basically those are your major ones that happen on the surface of the land. There's also something called evapotranspiration I want to talk about right here. All right, evapotranspiration is basically when roots take in water, or plants take in water, and then the water goes from their leaves. So this isn't exactly evaporation from just sitting water. The water is inside the leaves and it goes up into the air from the leaves, and this does happen. Then what happens about going into the water where we get our groundwater? So you have the surface runoff. The runoff happens on the surface, and that leads into oceans and lakes. But it also can infiltrate into the ground. It's called infiltration, and that's when it goes into the ground. It gets absorbed by the soil. This happens a lot better if there's plants around to take that in and create soil stability. And then basically it'll go down into the ground. It will form basically underground water channels and will collect under the ground, which becomes groundwater storage. And the groundwater will actually, it won't just sit there. It will actually flow into the ocean or gulf or wherever your lowest point is as well, as long as the level is higher than the ocean level, the sea level. So the level of the groundwater needs to be higher than the sea level, and therefore you can have a positive flow that way. If you have it the other way, if your groundwater goes down too low, you'll see that we can then have saltwater infiltration into your groundwater, and if you're pumping that out as your freshwater source, that's a big no-no. We don't like that, so you don't want to pull water out of this too fast. Of course, plants uptake it from the groundwater. Groundwater is extremely important, not only for us to take out, but for plants to be healthy as well. So this is going off over those different terms: evaporation, evaporating into the air, turning from a liquid to a gas; precipitation, turning back from a gas into a liquid and falling down; interception. This was not in the above graphic, but interception is on your A syllabus. That's basically where you have, you think about a football game. Interception is where the defense catches the football before it can get to where it's going. So it's the same thing. The plants intercept, and interception is where the plants intercept the water before it can hit the ground and absorb it. So it hit the leaves and it would never make it to the ground. Runoff is where precipitation falls and hits the ground and runs off to the lowest elevation. Infiltration is how it gets into the water, gets absorbed by the soil, and forms groundwater. All right. So the groundwater is recharged over time. Like I said, if the rate of water leaving the aquifer, and the aquifer is the area underground where the water is stored. So it's called groundwater and it resides in the aquifer. If the water leaving the aquifer, if you're pumping out faster than you're recharging it, the aquifer level will drop and will become inaccessible. The water table, if you find the water table is right here. This is basically an aquifer system. The water table is this point right here that you see labeled with the triangle. All right. The water table is the point at which the ground is saturated, so full to the max with water. If the water table is higher than the sea level, the fresh water will stay, like I said. However, if the aquifer is overdrawn, if you pull too much out and that water table starts to decrease because you're pulling too much out, you're going to then have saltwater infiltration and saltwater intrusion, which will make your groundwater salty, which will make it unusable for a freshwater source. So in this graphic, there are 3 different types of aquifers you do need to know. This has come up on the ACE exam before. Confined aquifers. Confined aquifers sit below an impermeable, that means an impenetrable rock hard, so it's basically a rock hard layer, or it could be clay that's really condensed and water cannot escape. These ones are recharged from a distance, usually under immense pressure because of the rock layer. And therefore, though, because it's under, so this is the confined aquifer, the bottom one here, all right, right here. All right, so what you have here is you have recharge from a far way away, but it pushes it down, puts a lot of pressure, and there's like basically a rock layer above, rock layer below, providing that pressure. Now, the cool thing about these are that if you tap them, there's so much pressure in there. Tap them means you drill a hole down into them. If you drill a hole down into them, there's so much pressure caused by those impermeable layers that water will flow out freely without a pump. All right, there's enough pressure to push it up and out. And these are called, when you drill a hole in there and you get water out, these are called artesian wells, which is really cool. All right. These ones are not usually very susceptible. These types of confined aquifers aren't usually susceptible to pollution because of how far away the recharge areas are. However, they're harder to get to. Unconfined aquifers are pretty easy to get to and pretty big. You can see there's not an impermeable layer above, so it's basically just like dirt and sand and soil above, and then the water will infiltrate directly in and fill these back up. Easier to get in, easier, faster to recharge than the confined aquifer. So they may have there's usually not a lot of pressure since there's no hard layer holding the water in. So when you do tap these, the disadvantage, while they are easier to get to and can have a good amount of water and don't take as long to recharge, the disadvantage is that you have to physically pump it out yourself, usually with electronic pumps. They're more susceptible also to pollution because of how close they are to the surface. And finally, a perched aquifer is where you have maybe some kind of rock that has formed in that permeable layer, and a small amount of water will just sit on top and get recharged over time. That's cool for like a home well or something like that, but usually not a lot of water there. So they're important because they're so close to the surface, so they're super easy to get to, and they can also be the source of natural springs. So that's the global hydrological cycle. Now, while the global hydrological cycle is a closed system means that nothing comes in, nothing comes out. The local system, so if you talk about like a certain state or a city or even a country, all those, I mean, really you probably go more of a state than the whole country, but the local systems are open systems, okay? Water gets stored in the ground or on the surface, may increase or decrease the amounts, can move to other regions, it can move in and out of Florida, so that's an open system. So that's the big thing to remember about local versus global. Local systems, you have to worry about other places. It's kind of like when we heard the case studies, and you heard about the Nile River, Tigris, Euphrates, you heard about Florida, Georgia, Alabama, how they all have to rely on each other, and that can cause conflict because they are sharing water and their systems are open. So one area can cut off the other area from their supply of fresh water. I would like you guys to click the link. Oh, maybe not. I'll look at that in a minute, and I'll try to fix that very soon today. All right, so that's it right now. Hopefully I can get that link to work to get you guys Florida's water cycle, so you can read about that a little bit more and put that in your back pocket for case studies. So that's it on 3-1-1.